In this section, we'll learn about expressions, statements, and operators in C++. Expressions are the building blocks of statements, and statements are the building blocks of programming in C++. You've already seen variable declaration statements and I/O statements, simple assignment statements, and even the return statement. First, we'll talk about expressions and statements in general and their role in programming. Then we'll learn about block statements or compound statements. This allows us to group multiple statements that belong together into a single unit. The last part of this section is all about the main C++ operators in the context of statements and expressions. We'll first discuss the assignment operator, which is the key element of an assignment statement. Then we'll look at C++'s arithmetic operators. These operators allow us to perform math very easily based on the math rules that we learned in school as kids. We'll then look at the increment and decrement operators. These operators are often used in C++ and can be confusing. I'll walk you through how to use them so it's clear. A common use case in programming is comparing two objects. We often need to know if one object is less than, greater than, or equal to another object, and based on that result, we decide what our next action will be. These are the relational operators. After the relational operators, we'll look at the logical operators. The logical operators allow us to embed complex logic into our program so we can solve difficult problems. If we put together expressions containing relational and logical operators, we can solve extremely complex problems. Then we'll learn about C++'s compound assignment statements. They allow us to perform an operation and assign the result of that operation using a simple syntax. Finally, we'll talk about operator precedence. Precedence determines in what order operators are executed. We've got a lot to cover in this section, so let's get started. In this video, we'll learn about C++ expressions and statements. Let's start with expressions. Expressions are the most basic building blocks in programming. Expressions are defined as follows in the C++ standard: a sequence of operators and operands that specifies a computation. We'll see some examples shortly, but for now you can think of an expression as a sequence of operands and operators that compute a value. That's a pretty simplistic view, but it will serve us well until we learn more advanced C++ features. Let's see some example C++ expressions. Let's start with the literal 34. That's an expression whose value is simply 34. Variables such as favorite number in this example are also expressions, since their value is the value of the variable. We can also have mathematical expressions, such as 1.5 plus 2.8, which will add those two numbers, and 2 times 5, which will multiply 2 and 5. There are many more examples of expressions, since there are many operators in C++ and we can combine them to make any expression we wish. If we wanted to test to see if A was greater than B, where A and B are variables, we can use the greater than sign between the A and the B. This evaluates to a Boolean, a true-false value. Notice the last example. This is an assignment expression. We are assigning B to A. This is also an expression because the value of this expression is what we just assigned. We'll talk more about this in a few videos when we talk about assignment statements in detail. Now let's see what makes a statement different from an expression. A statement is a complete line of code that performs some action. Statements are usually terminated with a semicolon. When you first learn C++, it's a very common error to forget to terminate statements with semicolons. Statements usually contain expressions. As you would expect, C++ has many types of statements. It has expression statements, the null statement, compound statements, and more. We'll discuss specific types of statements in the next several sections of the course. Let's see some example C++ statements. The first statement is the declaration statement, which we've already seen in this course when we declared variables. In this example, we declare x to be of type integer. The second is a simple assignment statement where we assign the literal expression 12 to favorite number. The third example is an expression statement. Note that it's simply an expression with a semicolon at the end. It's a pretty useless statement though, since we add two numbers but don't do anything with the sum. The fourth example is x equals 2 times 5 is an assignment statement. First we multiply 2 and 5 and store the product in x. Notice how expressions are used to make up the statement. The next example is an if statement. If statements give you lots of power to control the flow of your program. We'll discuss if statements in detail. But you can see that we're comparing A and B, And if A is greater than B, then we execute the statement that displays to the console. So here you can see an example of a statement that contains another statement within it and is also made up of expressions. The final statement is simply a semicolon. This is the null statement and performs no actions. You don't often use the null statement, but it can come in handy sometimes. C++ has a rich set of operators that can be used to build up expressions. Most of the C++ operators are binary operators, which means they operate on two operands, for example, the multiplication operator. However, some are unary operators, which means they operate on only one operand. An example of this is the unary minus operator, which simply negates its operand. There's even a ternary operator that operates on three operands. This is the conditional operator. The C++ common operators can be grouped into several categories. Assignment operators are used to modify the value of some object by assigning a new value to it. Arithmetic operators are used to perform mathematical operations on operands. The increment and decrement operators are interesting because part of them work like an assignment and part of them work like arithmetic. They're super useful and very commonly used. Relational operators or comparison operators allow you to compare the values of two objects. These are very useful and include equal to, not equal to, less than, greater than, and so forth. The logical operators are used to test for logical or Boolean conditions. For example, if you want to execute a specific statement only when the temperature is less than freezing and it isn't snowing, these include the logical not, and or operators. There are also several member access operators. We've already seen one of them. Remember the array subscript operator. It allows access to a specific member. There are others that work with objects and pointers, which we'll cover later in this course. Finally, there's the other category. This includes those operators that really don't fit very well into the previous categories. In the next several videos, we'll head over to CodeLight and see some examples of these operators in live code. Nearly all programming languages have the ability to change the value of a variable. In C++, we can change the value stored in a variable using the assignment operator. The assignment operator is a single equal sign. It's important to understand that this does not represent equality. In the code sample on this page, we are not asserting that the left-hand side is equal to the right-hand side, nor are we comparing the left-hand side and the right-hand side. In this case, we're evaluating the value of the expression on the right-hand side and storing that value into the variable represented by the left-hand side. C++ is statically typed. That means that the compiler will be checking to see if it makes sense to store the value from the right-hand side to the left-hand side. If it doesn't make sense, you'll get a compiler error saying exactly that. In order to store a value into the left-hand side must be assignable. It can't be a literal, it can't be a constant. If it is, the compiler will produce an error message. We can assign multiple variables all at once in a single assignment statement. This is possible because the assignment expression evaluates to what was just assigned. So it's easy to chain assignment statements together. Let's head over to the IDE and we'll work with the assignment operator in live code. Okay, so now I'm in the CodeLight IDE. I'm in the Section 8 workspace, and the project is called Assignment Operator. We'll go through some examples of how to use the assignment operator and the effects of the assignment operator in this video. So what I've done here is I've created two variables, num1 and num2. I'm declaring them and initializing them to 10 and 20 respectively. And then I've just got a simple output statement that prints out num1 and num2. Right now, this is not assignment. Right, what you see up here right now, and let me just mark that up. What you see here is not assignment, it's initialization. It's important to understand the difference. Initialization happens when the variable is declared and it gets that value for the very first time. Assignment is when you change a value that already exists in the variable. Okay, so let's try to change one of those values. I'm going to type in here just something really simple like num1 equals 100. You notice I just said num1 equals 100. This is one of the ways that programmers read this. Num1 equals 100. Assign 100 to num1. Move 100 to num1. you'll hear this sort of jargon, but often you'll hear num1 equals 100. And what we mean there is it's an assignment statement. We're not saying that num1 is actually equivalent to 100. This is an assignment statement. Num1 in this case is 10, remember. So what we're doing is we're moving 100 into that value. Okay, so let's break this down and go through this one step at a time so you really see what's going on here. What we're doing is, again, we have a left-hand side, an assignment operator, and the right-hand side. Right? That's an assignment expression. We put a semicolon in the end. Now it's an assignment statement. In this case, we're evaluating the right-hand side expression. In this case, it's 100. It's a literal. It's going to evaluate to 100. Okay. Now, here is my variable num1. Currently, it has a 10 in there. You can see that right there. I initialized it to 10. When we say something like num1 equals 100, or again, assign 100 to num1, we're evaluating that right-hand side. In this case, as I said, it's 100. And we're storing that 100 into num1. Okay. But num1 is 10. Yes, but when you use num1, this variable num1 on the left-hand side, we're using its location, not its value. In C++, there's the concept of L value and R value. And it gets pretty complicated when we're talking about more advanced features in C++. But at this level, it's really pretty simple. The R value is the contents of some variable, let's say. In this case, the contents of num1 is 10. So the R value of num1 will be 10. The L value is the location of that variable. So again, what this means is move 100 or store 100 into the location of num1. So what's going to happen is that we just changed the 10 to 100. Okay, again, conceptually, it's a pretty straightforward thing. So let me clear this and we'll run it. And what we expect now is we expect num1 to be 100 and num2 to still be 20 because we haven't messed with it at all. Let me compile and run. And you can see num1 is 100 because we changed it in the assignment statement, and num2 is 20. Okay, it's pretty simple. We don't have to use literals here. We can use anything we like. In this case, I could say num2. Okay, so remember, because this variable num2 is on the right-hand side of that assignment statement, we're using its R value or its contents. We're using the 20 basically. So we're taking the 20 and we're assigning it to the location where num1 is, that box where num1 lives. Okay? So it's going to change that guy to a 20. Okay? Or we'll put a 20 in num1, however you want to look at it. It all means the same thing. So now when we print these two values, we should get 20 and 20. So let's give it a run. So I'm building and running, and now we've got 20 and 20. Remember, we've got a left-hand side, the assignment operator, and the right-hand side, followed by a semicolon. This right-hand side could be really, really complex. I mean, it could be some really, it could be some really complex mathematical expression that just goes on and on and on and on. It doesn't really matter. What the compiler is going to do is going to evaluate this expression to some value. And then it's going to assign that value that was just calculated into that variable. The compiler does type checking for us. Remember, C++ is statically typed, which means that a lot of errors are caught by the compiler. This is very different from other languages like Python and Ruby and so forth, where they do all this type checking at runtime. C++ does it at compile time. So when the program is running, you're guaranteed that this is going to be correct because it's already done a lot of this checking for you. So what the compiler does now is it's going to check to see, does it make sense for me to assign whatever value is in here to here? How does it know? It's looking at the types. Okay, it's saying num2 is an integer, num1 is an integer. Okay, if I did something like num1 equals 200, it's going to say, okay, that's an integer. Does it make sense to assign an integer to an integer? Sure it does. It's got its rules internally. And we'll talk about mixed mode assignment and mixed mode math in a couple of videos from now. That's where we're adding and multiplying integers and real numbers and assigning potentially a real number to an integer. It's not just ints with ints, right? We've got different types working together. And that all works really well too, but we'll talk about that in a couple of videos. So that takes care of this. Hopefully you can see that conceptually it's really, really straightforward. Let's say that we wanted to chain these together. Okay, So what we can do here is we can chain those assignment operators together. And again, let's break this down so you can see what's happening. We're going to say num1, num2, and some value. It could be a big old mathematical expression, but in this case, I'm just going to use 1,000 to make things easier. Okay, so we've got two assignment operators here. What's important to understand with assignment operators and assignment expressions is that they return a value themselves. They return what was just assigned. Okay, and they associate right to left, which makes sense, right? In other words, this will be the last thing done. So the first thing the compiler does is it sees this expression right here. And it says, okay, I want to assign 1,000 into num2. Okay, let's do that. So num2 right here is going to get 1,000. Now the value that this expression evaluates to is 1,000 because that's the number that was just assigned. So now you've got num1 equals 1,000. So what we do is we assign 1,000 to num1. Okay, and now we're done. So you can see that you can chain these things together and they go right to left. So it's a handy way to initialize a bunch of variables to the same value. Again, we can have all sorts of expressions in here and so forth if we want. That's really not considered good practice. The only time that you really should even consider chaining these assignment operators is when you're assigning the same thing to everything. Right? Num1, num2, num3, num4 equals 10 or 0 or something like that. That makes sense. But if you've got really complicated expressions in these pieces here, that's probably not a good idea to do. Okay, so let's take a look at that and let's run this. And you can see now that when they print out, you get 1,000 and 1,000, just like you would expect. Num1 is 1,000, num2 is 1,000. Okay, let's do an error here. Let's say we wanted to do something like that. Now, the C++ compiler is pretty smart. And when we talk about classes and objects, we'll talk about how we can make the assignment operator our own so it works with our own classes. So as I said, C++ is pretty smart. It's going to try to see if it's possible to convert whatever's on the right-hand side to the left-hand side. In this case, you're telling the compiler, store a string, Frank, right, a sequence of characters, into an integer. That makes no sense. The compiler is going to try to see if it can convert that string to an integer somehow. And if it's got some sort of code that maybe you've written, it'll execute that code and convert it. In this case, there is no such code. So if I build and run this, I'm going to get an error. And the error is going to say invalid conversion from a character pointer. We'll talk about what that is in a few videos, to an integer. So again, it's a conversion issue. It's saying, I don't know, these are apples and oranges as far as the compiler is concerned. So let me clear this and let's do one more. And let's say I want to assign 100 to num1. We've seen that works fine, but what if num1 is a constant? So let's say we made num1 a const. This shouldn't be allowed, right? Because you've just said I've got a constant integer here, number 1, and I initialized it to 10, and now you want to change it to 100. Obviously, the compiler is going to say, whoa, wait a minute, you just told me that was a constant. I can't do that for you. So let's try that. We'll run it, and you should see an error. Something about read-only. There you go. Error, assignment of read-only variables not allowed. So you can't do that. Okay. Similarly, I can't do something like this. 100, let's say, equals num1. Right? What are you trying to do here? Your compiler is probably thinking, what in the world do they want to do? Okay, we know what num1 is, right? Its value, it's 10 because it's on the right-hand side. But now you want to assign it to 100. 100 is a literal. 100 doesn't have an L value. It doesn't have a location in memory. Okay, so when you run this, you'll see something like error L value required as the left operand of an assignment. I need to store this somewhere. I need a location. And 100 is a literal. It doesn't have a location. Okay, so that's it. Assignment at this level is pretty simple. We're going to use it at this level for a bit. Once we get to our own classes and objects, we can make assignment work for us in a really, really powerful way. And we'll talk about that when we get there. In the next video, what we'll do is we'll talk about the mathematical operators or the arithmetic operators, the plus, the minus, the multiply, the divide, and the remainder. In this video, we'll go over C++'s arithmetic operators. These are exactly the ones you expect. The plus symbol means addition, the minus symbol means subtraction, the asterisk is multiplication, the forward slash is division, and the percent symbol is the modulo operator, or the remainder of division. You may not be familiar with this operator, but that's okay. We'll cover it toward the end of the video. The plus, minus, multiplication, and division operators are overloaded. What that means is they'll work with different types. So we can add two integers, we can add two floats, we can add two doubles by simply using the plus symbol. The same is true for subtraction, multiplication, and division. The modulo operator only works with integers. And again, I'll show you an example of that in a little bit. So let's try a few examples here. In the code down here, you can see that I've declared two integers, num1 and num2, and I've assigned 200 and 100 to them respectively. Again, these are integers. You could do this with doubles or floats or anything you'd like, but I'm just going to use integers here. You can see that this first line, this first output statement right here, let's walk through that really quickly so we're clear as to what's going on here. Remember, we've got expressions here. So num1 is an expression, num2 is an expression, and that addition expression is evaluated to the sum of num1 and num2. So in this case, num1 is 200, so this will be replaced with 200. Num2 is 100, and this will be replaced with 100. And then num1 plus num2 will be added together. That's why the plus is there, and this will give us 300. Okay, now these guys are inside quotes, so they're string literals, and they'll be printed out as is. So what we expect here is 200 plus 100 equals 300, and of course we've got the new line, or the end line at the end. All right, so let's run this and see if we get what we expect. And exactly that's what happens. 200 plus 100 equals 300. Okay, so let me comment that line out. And what we could do is, rather than do that calculation right in line right here, we could simply do the calculation and assign it to a variable. In this case, let's create a variable called result. And we'll initialize it to 0. And all we're saying is add num1 and num2, that'll give us 300, and assign that result to the result variable. Okay, so we're going to add 200 plus 100, that gives us 300, and we're storing 300 into result. And then rather than do the calculation here as we did, we're just going to print out result. Okay, it's as easy as that. So when I run this now, I should have the same exact output. 200 plus 100 equals 300. So now let me comment out some of these, and we'll walk through these real quick. And I'll do it right up to there. So this next one here on line 29, I'm simply subtracting num1 minus num2, storing the difference in result, and then I'm outputting result. So here we would expect 200 minus 100, we'd expect 100. On line 32, we're multiplying the two. This is different from algebra. You have to have that multiplication symbol, that asterisk. You can't just say num1, num2, something like that, like you would do in algebra, where you just put the two things together. You can't use a dot like you could in algebra as well. It's got to be the multiplication operator, which is the asterisk. So we're going to multiply num1 and num2. That'll give us 20,000, which we store in result, and we're displaying that. And then the third one would be result is num1 divided by num2. That's on line 35, and we're going to store that quotient into result. There we would expect 200 divided by 100 gives us 2. Okay, so let's run what we've got right here and see what our results are. So we've got 200 plus 100 like we did before is 300. 200 minus 100 is 100. 200 times 100 is 20,000. And 200 divided by 100 is 2. Okay, so this is exactly like you would expect. It's really, really simple. Math works just like you expect it to. Now, something you may not expect is this result right here on line 38. I'm going to uncomment this. And in this case, what I'm doing is I'm dividing num2 by num1. Okay, remember, num2 is 100 and num1 is 200. So what's happening here is I'm dividing 100 divided by 200. You would expect 0.5. That's not what you get. We're doing integer division. Okay, so there are no digits after the decimal point. We're working with whole numbers only. So in this case, what happens is 100 gets divided by 200. And the result, if these were doubles, would be 0.5. but we're working with integers, so this piece is just chopped right off. So we end up with a 0. Okay, so let's run this. And you can see here 100 divided by 200 is 0. You've got to be really careful when you're doing division with whole numbers or integers, because this is the behavior. If you need the 0.5, you want to be really, really precise, then you need to use doubles, not integers. And I'll show you an example using doubles in a second. Now let's look at the modulo operator, or the remainder of operator. In this case, right here, I'm saying num1 mod num2. Again, what's num1? It's 200. What's num2? 100. So 200 divided by, let me write that out real clear so it's not confusing at all. So we're going to say 200, right, divided by 100. The result of this is 2 with a remainder of 0. That's the modulo operator. It's only interested in the remainder. So in this case, it'll print out a 0. The next line, I'll uncomment that out in a second, but the next line we're going to say right here, num1, let me clear that, draw that line a little nicer there. Here we're saying num1 mod num2. So we're saying 10 mod 3. Remember, this only works with integers. So the result here of the division will be 3 with a remainder of 1. Remember, 3 times 3 is 9, and you get the 1 remainder. That's the result of the modulo operator. It's a pretty handy operator. So let me clear this, and I'll uncomment these few lines of code right here. And we'll run this. And let's take a look at the result. So here we go. 200 mod 100 is 0, right? That's the remainder, because we get a 2 with a remainder of 0. And in this case, 10 mod 3 is 1, because we get a 3 with a remainder of 1 when we divide by 3. This can be a really, really handy operator to use. And in the challenge exercise, you're going to have to use it to solve the problem. A couple more things. Just like you can with any programming language and doing any kind of math, we can add and divide and subtract, and we can do everything in line. It's important to understand that the precedence, or the order in which this stuff happens, is the same precedence you probably learned in grade school. Here in the US, we learned PEMDAS. That was the acronym we used, which meant parentheses first, then exponents, then multiplication and division, and then addition and subtraction. You may have learned something else if you're from a different country, but that's what we learned here. So what this means is that multiplication and division happen before addition and subtraction, right? So in this case, what's going to happen is num1 is going to be multiplied by 10, and then we're going to add num2 to that result, right? If you want something else, if you want to add the 10 and the num2 first, then you need to use parentheses around there like that. It's as simple as that, and it's something that we're all used to by now. Let me clear this, and then I'll do this last example with the division. I'll comment these two lines out. So in this case, I'm outputting 5 divided by 10. Remember, this is using integer division, so 5 divided by 10 is 0, not 0.5. In this case, 5.0 divided by 10.0 is 0.5 because we're using doubles here. In a couple of videos from now, we're going to do a video where we're mixing types. We'll be multiplying and dividing integers and doubles all together on the same expression. In that case, we can use casts to tell the compiler, hey, you know what? I really want this to be a double instead of an integer, even though it looks like an integer there. Okay, so we'll get to that in a minute. And let me run this thing one more time. And you can see the last two results right down here. 5 divided by 10 is 0, and 5.0 divided by 10.0 is 0.5. Okay, so now let's solve a real problem. Let's convert euros to US dollars. And I've created a project in the Section 8 workspace called Euros. This project that I worked on right here is called Arithmetic Operators, so you can refer to that if you like. But I've created a project called Euros, and that's the one we'll get to next. Okay, so I've opened up the main CPP file in the Euros project. Right now, there's really not much in here. I'm just printing a new line at the end to separate that little time message that is displayed at the end. And there's no real code here. We're going to write the code from scratch. So what we want to do is we want to convert euros to US dollars. So obviously we need some sort of conversion factor. I just went on Google now and I saw that you have $1.19 per euro. Okay, so 1 euro is $1.19. So we need to use that value somewhere. Now that's going to be a constant. So let's define that as a constant. We can do it right here. We could say const. We want it to be a double, right? Because it's not an integer, it's 1.19. And we'll give it a name. We'll call it US dollars per euro, per EUR. And we'll initialize that to 1.19. And don't forget the semicolon. So now we've declared that constant US dollars per euro to be 1.19. It's not going to change even accidentally. Now, what do we need to do? Well, we need to output a message to the user. We'll say cout. We'll say welcome to the EUR to USD converter or something like that. And we'll put an end line at the end. We need to ask the user to enter the value in euros, right? I mean, that's the whole idea. So cout, we'll say enter the value in euros. And we'll do something like that. We won't put a new line there because we want the user to type something in right next to it. What do we do next? Well, we need to do a few things. We need, remember, most of these programs are input, processing, and then output. We need input. We need to read in from CN the number of euros that they want to convert, right? So we need to have something like CN into euros. So we need to define that variable right here. Right, so let's do that right in here. We'll say double. We'll call it euros. That's a good name. And we'll initialize it to 0.0. That way we know we've got a zero value in there. We know we're going to convert this to dollars, right? So we may as well create our dollars variable as well. So we could say double. And we can call it dollars. And again, 0.0. Perfect. Now we're right in the euros. We need to convert the euros to dollars. How do we do that? We just use a real simple multiplication. We can say that the number of dollars is equal to, again, the number of euros times the constant we have, dollars per euro. And now all we need is that final output statement. Let me scroll up just a little bit. And we'll say something like cout, and we'll say the euros, whatever they entered, is equivalent to, or we'll actually say euros. That'll be nice so they can read it better. Is equivalent to, we'll put another insertion operator here. We'll type in dollars, whatever the conversion was, and then we'll just type the string dollars so it's nice and readable. That's it. We'll put a new line at the end with end line, and that should be it. Let's run this and see if we have any errors. We'll test it to make sure we don't have any errors, and we'll debug it if we do have any errors. All right, so I'm going to save, and I'm going to press Control F5 to run. There's no compiler errors, so that's great. So enter the value in euros. Well, let's type in 1 euro, right? If we type in 1 euro, we expect back $1.19. So that would be a real simple and good test case. We get 1 euro is equivalent to $1.19. Good. Let's try another one. Let's run. How about 123.5 euros? We get back $146.965. Don't worry about the precision and the dollars and cents. We'll learn how to format output a little bit later. That's it. That's the program. Really, really simple. You can see that what we're doing here is we're using the things that we've learned, right? We're using our cin, we're using our cout. We've got a constant defined right here. We've got some variables that we need here, and we're initializing them to 0. And we're doing our calculation here using one of the arithmetic operators, the multiplication symbol. I encourage you to write one of these programs on your own. Write a something to something converter, Fahrenheit to Celsius, kilometers to miles, yards to inches, meters to centimeters. Write one of these programs just like that. That'll give you a good practice. In this video, we'll go over C++'s increment and decrement operators. I'm in the Section 8 workspace in the increment-decrement operators project. This is a pretty simple looking operator, but there's a lot to it, and it can be extremely confusing if you overuse it. Let's talk about it. Basically, it's the plus plus and minus minus operator. You've got two pluses side by side or two minuses side by side. All that means is increment something by 1 or decrement something by 1. In this example, I'm only going to be using the increment operator, but everything will apply to the decrement operator. Okay, so all it does is increment or decrement its operand by 1. So if you use it with an integer, it increases the integer by 1 or decreases the integer by 1, depending on which one you're using. If you're using it with a floating point number, same thing. It'll increase it by 1 or decrease it by 1. And we can also use it with pointers to move pointers along. We haven't talked about pointers yet, but we'll use this operator when we talk about pointers in a future section. There are two variants to this operator. There's a prefix notation and a postfix notation. All that means is that the operator is either before its operand or after its operand. You can see here on line number 9 that the operand is num and the operator is to the left of it. So that's prefix notation. The postfix notation is when it appears to the right of the operand. Okay, I'll say this a few times. Don't overuse this operator and never use it twice for the same variable in the same statement because the behavior is undefined. You really don't know what you're going to get. Good. So now let's talk about the operator. Let me scroll down just a little bit. And I've got some examples here, and I'll walk through these examples really carefully and slowly so you can understand what's going on. For all of the examples, I'll be using these two variables right here. I'll be using a variable called counter and a variable called result. They're both integers. Counter will be initialized to 10 and result to 0. Okay, so real straightforward. Counter will be 10, result will be 0, and we're going to manipulate those variables, and we'll see how this operator really works. So let's start right here. Let me uncomment example 1. I'll walk through this really slowly. You can see what's happening. I'm outputting counter. Okay, well, counter is 10, so this you expect it to display a 10, and that's exactly what happens. In this case, I'm saying counter equals counter plus 1, right? So what's counter? 10. I'm adding 1 to it, and then I'm putting it right back into counter. So I'm changing this to an 11. And this output statement will display an 11. In this case, I'm using counter plus plus. That's the increment operator. That's going to increment the variable counter by 1. When you use it all alone like that, if you've got an operand followed by a plus plus or a plus plus before the operand, it means exactly the same thing. All it means is increment the operand by 1. Okay? It'll get a little more confusing in the next few examples, but let's just get this one under our belt so we can understand what's going on. So what's happening here is we're incrementing that L value counter by 1. So we're going to counter, incrementing it by 1. Now it's 12. And we're going to display counter here, which is 12. The pre-increment works exactly the same as the post-increment when that thing is all alone on a line, just like I said over here. So in this case, exactly the same thing will happen. I'm going to take the 12 and add 1 to it, make it a 13. Counter will now be 13, and I'll output 13. All right, so in this context, wherever you want to increment something, you could say counter equals counter plus 1, or you could just say counter plus plus, or you could say plus plus counter. All three of them mean the same thing. Later on, we'll talk about a different operator, the plus equals operator, that does the same thing as well. So there's a bunch of different ways that you can achieve the same result. I'm going to clear this, and remember, we've got 10, 11, 12, and 13 as the output. So I'll clear this, and let's run this example. And you can see that counter is 10, 11, 12, and 13, just like what we expected. All right, so now let's look at a little bit more complicated example, and I'm going to comment this out, and I'll comment this out, not delete it, and I will uncomment out example 2. Okay, so let's go through this one again really carefully. What we've got here is, again, I've reset counter to 10, and result to 0. All of these examples are going to start in the same place. Counter will be 10, result will be 0. So here I'm going to say I want to output counter. Well, counter is 10, right? So we expect this to display a 10. Now we're doing a pre-increment of counter, and we're storing the result into that variable called result. So what's happening here is there's really a few things going on here. If you just see that plus plus and just take it out for a second, and the result is something like this. Result equals counter. That's the real assignment statement that's going on here. The plus plus in front of counter means it's prefix notation, which means that counter will be incremented before it's used. So in this case, before happens here. Its use is right here, but before it's used, we're going to say counter equals, I'll just say counter plus 1 just to be really explicit. So this statement right here, that's the effect of that statement. I want to increment counter before I use it, and then I want to use it by assigning it to result. All right, so let's do those two steps and see what happens. Counter equals counter plus 1. We just made counter 11. And then we're going to assign counter to result. Well, counter is 11, so result will now be 11. Now I want to display counter. Counter will be 11, and result will be 11. So this is what I expect as the output, 10, 11, and 11. Okay. Remember, this is the use, and this is the effect of that pre-increment. All right, so let me clear this and run it. Again, we're expecting 10, 11, and 11. I'll build and run. And there it is, 10, 11, and 11, exactly what we expected. All right, I'll comment out that piece, and we'll do another example, this time with a post increment. And remember, I'm using the increment, but the decrement works exactly the same way. It just decreases the value by 1. All right, I'll uncomment this example, and let's walk through this one again. One more time, I'm initializing count, or I'm assigning 10 to counter and 0 to result. And I'm saying print out the counter. Well, it's 10. We expect a 10 here. That's an easy one. But now we're doing a post increment. Notice it's on the right side, or it's following counter, its operand. So this becomes result equals counter. And the post increment simply means that we're going to increment counter after we use it. Well, we're using it here, so let's increment it after this time. So again, I'll be really explicit here, and I'll say counter equals counter plus 1. So that's the effect of that statement. So let's execute this statement. Result is counter. Well, counter is 10, so let's put 10 in here. Now we increment counter by 1. So that becomes 11. And now we display counter, which is 11, and result, which is 10. So in this case, this is the output we expect, 10, 11, and then 10. All right, let's give that a shot. And there we go, 10, 11, and 10. Let's do a few more examples, so I want to be sure that you really understand this. Let's uncomment example 4 here. And example 4 just uses the expression that's a little bit more complicated. Not much, but a little bit, so you can see how this works. In this case, one more time, I've set those to 10 and 0, and I'm displaying counter. Well, counter is 10. Again, real easy. And now we've got this statement going on right here. Result equals plus plus counter plus 10. The best way to really look at these things is just get rid of that guy right now. So just say result equals counter plus 10. That's the statement. And now, since the plus plus is a pre-increment, it's on the left side of counter. That means that we increment counter before we use it. We're using it here, so that means that we do this before we execute that statement. So again, counter equals counter plus 1. All right, so let's do this. Counter is counter plus 1. This becomes 11. Then we say result is counter plus 10. Well, counter is 11. So 11 plus 10 is going to give us a 21, which we're going to store in result. So result here, we'll get a 21. Got it? Perfect. Now, we're displaying counter. It's 11. Result is 21. That's what we expect to display. 10, 11, and 21. This may seem a little contrived and puzzle-like, and it may be, but this kind of code is seen out there, and you really need to understand the effect of the pre-increment and the post-increment with these operators. So 10, 11, and 21 is what we expect. Let's run this. And 10, 11, and 21 is what we get. Okay, so let's comment this one out. And you'll notice what this one, the next one, example 5, is exactly like example 4, except we've got a post increment right here. Right there, you can see it's the same idea, except it's the plus plus is after the operand. Okay, so again, 10 and 0, we're starting out. We're saying display the counter. Well, the counter is 10. That's pretty easy. Here's the statement. Let's just rewrite it without the increment. So we're going to say result equals, again, counter plus 10. I'm trying to write nice and big, so hopefully everybody can see this okay. And we're doing the increment of counter after we use it. That means after we use it. We're using it here. So this becomes counter is counter plus 1. All right, so let's execute these two statements. We'll put some semicolons there just to be complete. So result is counter plus 10. Well, what's counter? Counter is 10. So that becomes a 20, and we're storing 20 into result. And then we're incrementing counter by 1, so counter becomes 11. Okay, the output says what's counter? 11. What's result? 20. So in this case, 10, 11, and 20 is what we expect. 10, 11, and 20. Let's run this. And 10, 11, and 20 is exactly what we get. Okay, so hopefully that clears it up. And one of the examples, if you remember up at the top, I mentioned, I'll scroll up a little bit, it says here, never use it twice for the same variable in the same statement. That could be something like, suppose you do C out, and you've got something like, I don't know, let's just say we have an integer I. You'll say I plus plus, and then you'll do something like plus plus I. And something like that, you really have no clue what's going to happen because you're incrementing I 2 times in the same statement, and that's not a good idea. Sometimes you'll see people do silly things like I plus 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 I or something like that, just because you can in C++. But that's a bad thing to do because you're using it twice on the same variable in the same statement, and that behavior is totally undefined. So your guess is as good as mine as to what the result is going to be. Okay, so hopefully this gives you a little bit of insight into this operator. It's a simple operator when you just say I plus plus or count plus plus or plus plus count. Really, really simple. But when you start combining it with other operands and other expressions and operators, it can get pretty complicated. And that's why I say don't overuse this operator. It's really a great operator to use when we loop, and we'll do that later and when we use pointers. But keep your eye on it. Don't overuse it. In this video, we'll go over the C++ equality operators. These operators compare the values of 2 expressions and evaluate to a Boolean. That's a true-false value. The operators are the equals, which is represented by 2 equal signs, and the not equals operator, which is represented by the exclamation point or bang symbol, followed immediately by an equal symbol. Be extra careful when you're starting. It's super common for beginning C++ programmers to use a single equal sign. That's assignment, not comparison. These simple operators, along with the operators we'll learn about in the next several videos, give us so much power in programming. We use these operators all the time in control flow statements that we'll learn shortly. So suppose we want to do something when x is equal to 100. We can do that. We can also test for 2 expressions not being equal. So if my password doesn't match the password on file, then you want to do something specific. The following code snippets only show the equality expressions. They're always used within statements. The first example evaluate to true if the value of expression 1 is equal to the value of expression 2. These 2 expressions could be very complex or very simple. The second example will evaluate to true if the value of expression 1 is not equal to the value of expression 2. The third example will always evaluate to false, since 100 will never equal 200. We don't usually write expressions like these, but it serves to illustrate how this operator works. The final example evaluates to true if num1 is not equal to num2. Let's go over a few more examples that use statements. First, we're declaring a variable named result that's of type Boolean, and we're initializing it to false. Then we compare 100 and 50 plus 50 for equality. This will result in a Boolean that's a true-false value which we assign to result. In the next example, we compare num1 and num2, and if they're not equal, we store true in result, otherwise false. Notice how we can use Boolean expressions in output statements. In the first output statement, we're comparing num1 and num2, and we're displaying 1 if they're equal or 0 if they're not equal. Sometimes it's handy to display the words true and false rather than 1 and 0 in the output statements. We can do that using the bool alpha stream manipulator. Bool alpha and no bool alpha are located in the standard namespace. Once you use them, all Boolean output to the stream will result in the words true and false being displayed. That can be pretty handy. If you want to go back to the default of 0 and 1, just use no bool alpha. Let's head over to CodeLight and see some examples. So I'm in CodeLight. I'm in the Section 8 workspace, the Equality Operators project. Let's run over a few examples of using these equality operators. These are going to be really straightforward examples. I don't think you'll have any issues understanding these, but you may see a couple of surprises, so stay tuned for that. So here we go. We've got a Boolean called equal result, which I'm initializing to false, and another Boolean called not equal result, which I'm also initializing to false. And I've got two integers here, num1 and num2, and we'll just play around with this a little bit. I've got my cout bool alpha here commented out. I'll uncomment that out in a moment so you can see the difference between the behavior when you do that. So here I'm prompting the user to enter two integers separated by a space. I'm reading in those two integers on line 15. I'm comparing those two integers for equality right here on line 16. So I'm saying is num1 equal to num2. That result is going to be stored in equal result. So it's either going to be true if they're equal or not true if they're not equal. Then I'm going to compare the same two numbers using the not equal operator. So is num1 not equal to num2? In this case, if they are not equal, then I'm going to store true into the not equal result. Otherwise, false. Okay? And then I'm just going to print out those two results. So let's run this piece of the code right now, and you'll see what happens. Let's enter two integers. In this case, let's enter two integers that are equal to one another. So I'll type in 10 and 10 and press enter. And you can see here the comparison result for equals is 1, which is true. And for not equals, it's 0 because they obviously are equal. Okay, now notice I have a 1 and a 0 being outputted here. When I uncomment out the bool alpha stream manipulator and recompile and run, now I can say, let's say 2020. And instead of 0 or 1, we see true, false. So that's pretty handy. So in this case, they are true, so the equals will be true and the not equals will be false. Now let's use an example where they are not equal. And let's say we're trying to do 10 and 20 this time. So equals is false and not equals is true, just like what we'd expect. Okay, so like I said, that's pretty straightforward. I'm going to comment out this piece of code right here. And now we'll do the same thing, except we'll do it with characters. Remember, we can do this with any type. We can compare any type. So in this case, I've declared two characters, char1 and char2, and initialized them both to empty, to 0. And I'm asking the user to enter two characters separated by a space. I'm reading in the characters. Then I'm doing exactly the same thing. I'm comparing them for equality, and I'm comparing them to see if they're not equal. So let's run this. And the first test we'll do is we'll say lowercase a and uppercase a. Those are different characters. I'll press enter. Are they equals? Nope, that's false. Are they not equals? True, that's true. So that's exactly what we expect. And let's test it one more time with, let's say, a capital Z and another capital Z. In this case, they are equal. So that's true, and the not equals is false. Okay, so you can understand the logic that's going on here. I'll comment that out, and I will uncomment the next section, which is dealing with doubles. So again, exactly the same thing, except I'm using doubles. I'll run this, and we'll type in, let's say, two doubles that are the same, 12.1 and 12.1. The comparison result is they are equal. Exactly what we'd expect again. And let's do an example where they are not equal. So let's say 12.5 and 13.2. The equals is false because they're not equals, and the not equals is true because they are not equals. Okay? Now, this is the example that I wanted to run to show you something that may not be real obvious. Let's say we want to enter two doubles separated by a space. So I'm going to type in 12.0 and 11 point, lot of nines. Now to us, those are not the same number. But remember the way the computer stores floating point numbers, it stores approximations. So that might be surprising. As far as the computer is concerned, those numbers are equal because the representation that it's using to store them behind the scenes is equal. Okay, so it's important to understand that. If you're dealing with applications that need this kind of precision, scientific application, medical applications, many safety critical type applications, you would not use these built-in doubles. We would use specific specialized libraries that really help us deal with this so that 12.0 is not equal to 11.99999. Okay, so it's important to understand that, but the way that it stores it is an approximation. So as far as the computer is concerned, these are the same. So let's do one more, and I'll leave that double declaration there, and I'll uncomment this last piece of code here. And here I'm just grabbing an integer and a double. So we're doing some mixed mode comparison here. I'll run it. And it says, give me an integer and a double separated by a space. In this case, I could say 10 and 10.0. Remember what happens. It's using an operator to compare two different types. It doesn't want to do that. Those types have to be the same. So the 10 will be promoted to a 10.0. And then the comparison happens. That's the mixed mode expressions. So what we're doing here is we're eventually comparing 10.0 and 10.0. So we expect this to be true. And it is right there. And you get the same sort of issue here if I say 10 and 9.999, a whole bunch of nines. What's going to happen again is the 10 will be promoted to 10.0. 10.0 and 9 point, a bunch of nines, as far as the internal representation is concerned, are equal. So there's your true. Okay, so that's it. That finishes off this video. And that's it. I'll see you in the next video. In this video, we'll look at C++'s relational operators. In addition to the equality operators, C++ also has several other relational or comparison operators. These are greater than or equal to, less than, and less than or equal to. And in C++20, there'll be a really neat three-way comparison operator. This operator compares two expressions and evaluates to 0 if they're equal, less than 0 if the left-hand side is greater than the right-hand side, and greater than 0 if the right-hand side is greater than the left-hand side. Like the equality operators, these operators are very intuitive, easy to use and understand. Let's see a few examples in CodeLight. I'm in CodeLight. I'm in the Section 8 workspace, and this is the Relational Operators project. In this project, I'm just using some really simple examples to test some of these relational operators. As you can see, I've got two numbers declared, num1 and num2. This is where I'm going to read some integers into. And I'm asking the user to enter two integers separated by a space, and I'm reading those two integers from the user. Okay. Then what I'm doing in this output statement right here is, suppose that the user entered 10 and 20 here. I'm just saying 10 greater than, I'm just explicitly printing out that greater than sign, 20, and then I'm evaluating whether num1 is greater than num2, and that's going to say true or false. So it's going to do that for all four operators, greater than or equal to, less than, and less than or equal to. And then we could try out a couple of examples with this program. So let's run it. And let's enter two integers. Okay, so let's enter 10 and 20. So you could see here, 10 greater than 20 is false. 10 greater than or equal to 20 is false. 10 less than 20 is true. And 10 less than or equal to 20 is also true. Okay, so now let's try some other ones. A couple of other test cases here. Let's try 20 and 20. In this case, you can see that 20 is not greater than 20. 20 is greater than or equal to 20. 20 is not less than 20, and 20 is less than or equal to 20. Just what we'd expect. So real simple example. What I'll do now is I'll comment out those output statements that we just did here. And I'll declare a couple of constants here, and I'll uncomment this piece of code out, and I'll walk you through it. So in this case, I'm declaring two constants, lower and upper, to be 10 and 20. And I'm asking the user to enter an integer that's greater than lower. So in this case, I'm asking them to enter an integer that's greater than 10. And I left those as constants so you can modify them here and play around with this program yourself. So in this case, enter an integer that's greater than 10. I'm reading that integer into num1. And then I'm comparing to see if that number is greater than the lower limit, which is 10 in this case. Then I'm doing the same thing. I'm saying enter an integer that's less than or equal to the upper limit. So let's run this. And first thing you'll see is it says enter. Oops. Let me get rid of that. Let me get rid of that statement at the beginning here. And we try that again. Here we go. So enter an integer that's greater than 10. So let's print 12. And it says 12 greater than 10 is true. That's what we expect. Now it says enter an integer that's less than or equal to 20. Let's put in 12. And it says 12 less than or equal to 20 is true. Okay, so let's run this one more time with a different test case. So enter an integer that's greater than 10. Let's put in 8 this time. And it says 8 greater than 10 is false. Obviously, I didn't do what I was told to do. And here, enter an integer that's less than or equal to 20. Let's put in 25. And we can say 25 is less than or equal to 20 is also false. Okay, you can see where we're going with these operators. Once we get to control flow statements, you'll have all this knowledge under your belt, and you'll really be able to write some really powerful programs that solve problems. In this video, we'll learn about C++'s logical operators. These operators allow us to build complex conditions in our programs. C++ has three logical operators. These are not, and or. These operators work on Boolean expressions and evaluate to a Boolean value themselves. There are several ways to write these operators. You can use the keyword-like syntax using the words not, and or. Or you can use the operator symbol syntax using the bang sign, the double ampersand, and the double pipe symbol, or the double vertical bar. Personally, I've never seen any C++ code that uses the keyword-like syntax, so I'll use the operator symbol syntax in this course. Let's quickly review Boolean algebra by using a truth table. The logical not operator simply negates the result of the expression it's applied to. Note that this is a unary operator since it only works with one operand. So if the expression A is true, then not A is false. And if the expression A is false, then not A is true. Let's look at the logical AND. The logical AND is a binary operator, and it's only true when both its operands are true. So you can see in the table when expression A is true and expression B is true, then A and B is true. A and B is false for all other combinations. Finally, let's look at the logical OR. The logical OR operator is also a binary operator. The value of the logical OR is true when either expression is true. So the only time it's false is when both expressions are false. Using just these three logical operators, we can write some pretty complex logic. And if we combine the logical operators with the relational operators, we're in great shape to begin to solve many, many problems. Let's see what happens when we combine these operators together in an expression. Just like we had to understand precedence with the mathematical operators, we need to understand precedence for the logical operators. Logical NOT has the highest precedence, followed by logical AND, followed by logical OR. Of course, as with mathematical expressions, you can use parentheses to achieve exactly the behavior you're looking for. Let's wrap up logical operators by looking at a few example expressions and then talking about something called short circuit evaluation. Here are a few examples of logical expressions. In the first expression, we're determining if num1 is greater than or equal to 10 and less than 20. Notice that we use num1 in both expressions. We can't just write num1 greater than or equal to 10 and less than 20. We have to write num1 greater than or equal to 10 and num1 less than 20. Since we have an AND, both expressions must be true for the entire expression to be true. In the next logical expression, we're using a logical OR. In this case, either expression or both can be true for the entire expression to be true. So if num1 is less than or equal to 10, then the entire expression will be true. Also, if num1 is greater than or equal to 20, then the entire expression will be true. Notice how both expressions cannot be true, since num1 cannot be less than 10, and it can't be greater than or equal to 20 at the same time. The next logical expression is checking if it's not raining and the temperature is greater than 32 degrees Fahrenheit. The following expression uses a logical OR, and it will be true if it's raining or if it's snowing. Finally, the last logical expression is checking to see if temperature is greater than 100 and it is humid or it's raining. Remember here that the AND has precedence over the OR. I think you can see how powerful our logical expressions can be by simply combining these primitive operators. Also notice how important our variable names become as well. Let's finish up by discussing short circuit evaluation. C++ will stop evaluating a logical expression as soon as it knows the result. For example, suppose we have an expression like the first one, expression 1 and expression 2 and expression 3. If expression 1 is false, then there's no way that the entire expression can be true, since all the expressions must be true. So why bother evaluating expression 2 and expression 3 when the compiler already knows that the result will be false? This is called short circuit evaluation, and it's commonly used in many programming languages. Programmers take advantage of this behavior to optimize their code. In the second example, if any of the expressions is true, then the entire logical expression is true. So if expression 1 is true, then the compiler already knows that the entire expression is true, and it won't evaluate expression 2 or expression 3. However, if expression 1 is false, then the compiler continues evaluating expression 2 since it doesn't know the result yet. We'll use logical operators in depth when we learn about control structures. But for now, let's head over to CodeLight and see a few simple examples in live code. I'm in CodeLight in section 8 workspace, and I'm in the logical operators project. In this project, we'll go over a few examples of using logical operators. Let's start with a really simple one here. What I've got is I'm going to use this variable num to read numbers into just simple integers. I'm going to establish a range where the lower end is 10 and the upper end is 20. So that'll be like a number line where this will be 10 here and this will be 20 over here. Now, I'm going to ask the user to enter an integer and tell them what the bounds are, 10 and 20 in this case. Then I want to be sure that that number they entered is within the bounds. And I just want to display true or false if it's within the bounds. And what we're doing here is we're going to say not inclusive of 10 and not inclusive of 20. Okay, so it's going to be 11 to 19 inclusive. All right, so that's what we're going to do. Now, we're going to store that true or false value in this variable right here called within bounds. And here's our formula. Here's our expression right here. Basically, we're going to check to make sure that num is greater than lower. So num is going to be greater than lower. So suppose that user typed in 15. We want to make sure that it's greater than lower, and we want to make sure that it's less than upper. So we want to be sure that it's in here somewhere. Right? So that's where we've got that logical AND condition. So we'll do that, and then we'll simply print out the number is between lower and upper, and then true or false. And we can just display within bounds here. So let's run this with a couple of test cases. And here we go. Enter an integer. The bounds are 10 and 20. Now let's enter an integer that is within those bounds. 15 is right in the middle. And we'll press enter. And the result is 15 is between 10 and 20, true. Okay, so let's run another test case. Let's go off the right side to 22. Now we would expect a false. 22 is between 10 and 20, false. Let's do a test case on the left side. We'll go 5. We also expect a false. And that's what we've got. And then don't forget to test those edge cases, the 10 and the 20. So let's try 10. We expect false, right? Because being on 10 is not being between 10 and 20 in this case. So I get back a false. And the last test case we could run is 20. And we also expect a false, and that's what we're getting. It's very common to have these errors where instead of checking greater than here, you're doing greater than or equal to when you should be doing greater than and so forth. So you've got to be sure to test your code. Okay, so that's a simple example of testing to see if a number is between two numbers. Now, let me comment that out, and we'll do another example here. And of course, we're assuming that lower is less than upper in all of these examples. Okay. Now, what we want to do on this one is we want to test to see if the number is outside the bounds. Okay, so I want to be true if the number is outside the bounds. So we'll do the same idea here, right? We've got the line, and here's the 10, and here's the 20. And if the number's over here somewhere, we want a true, and if the number's over here somewhere, we want a true. Okay. Now we could just simply negate the previous result, right? So if the number is in here, if the number is not in here, then it's obviously either here or here. Right? But what we'll do is we'll do it explicitly. We've got a variable called outside the bounds, and we're going to check to be sure that number is less than lower. So that's taking care of this bit right here. Or number is greater than upper. There's no way we can use an and here. That would be a mistake, right? Because the number will never be less than 10 and greater than 20. That won't happen. It's impossible. So that would be a mistake, and that's a pretty common mistake, but you'll find it when you test. And there's your or. So let's run this example. And in this case, the bounds are 10 and 20. So let's say we want to go 25. Now, we expect true now. And that's what we're getting because 25 is outside of 10 and 20. Let's try the lower end. Let's try 5. That's also true. And let's try a number in between. 15 here. We expect that to be false, and it is because 15 is not outside the range. And then we could test with 10 and 20, and I'll leave that up to you guys. Okay, so let me comment that out. And the third example is actually checking to see whether the numbers are right on the bounds, whether they're 10 or 20. So what we're doing here, again, is we've got the line, got our number line, and we've got 10 over here and 20 over here. And we want to be sure if we want to return true if it's 10 or if it's 20. Okay, right on the bound. So we've got another variable here called on bounds. I'm setting it to false. And the condition is really simple. If the number is equal to the lower, that's it. So if the number is 10, or the number is equal to the upper. Okay, so if we've got a 10 or a 20 in this case, because that's what lower and upper are, this will return true. Remember, it can't be 10 and 20, so we need the or here. And with the or, if either piece is true, the entire thing is true. So let me clear this, and we'll run this example. So we should get back true for 10 and 20. So here's 10. There we go. We've got a true. We'll run it again with 20. That also gives us true, and everything else should give us a false, right? No matter what we put in. Let's put 15. We could put a false, and you could use some test cases outside 20 and less than 10 to check it out as well. So hopefully you're with me here. That's pretty straightforward stuff, but pretty powerful stuff. This is how you do input validation. You're asking a user to enter a number between something and something, or enter the amount of your check. Obviously, they're not going to enter negative numbers, and there may be a limit as to the upper end, so you can validate your data, because if you have bad data, you're going to get bad results. Now, in this case here, I'll comment all of this out, and I'll go through it and explain it to you. Okay, so what we've got here is and let me comment that bit out as well. All right, so here's where we're at. Here's the idea. We want to determine if you need to wear a coat, and that determination is based on the temperature and the wind speed. So I've got a Boolean value, and that Boolean value right here is going to be wear coat. That will be true or false, whether you need to wear a coat or not. And I'm going to read two variables in from the user. I'm going to read the temperature in Fahrenheit and the wind speed in miles per hour. And here are my limits. So wind over this value requires a coat. So if the wind is over 25 miles an hour, I need a coat. And the temperature below this value requires a coat. So if the temperature is below 45 degrees Fahrenheit, you need a coat. Okay, but we're going to test this two different ways. We're first going to use an or condition, and then we're going to use the and condition. Okay, so for the or condition, what we're saying is that if the wind speed is greater than 25 or the temperature is less than 45, you need a coat. For the and condition, we're going to say that the temperature has to be less than 45 and the wind speed has to be greater than 25. Okay, and the conditions are pretty much, I hope, what you would expect at this point. You can see what we're doing here. We're setting for the or condition. We're setting it right here. We're checking, obviously we're reading the temperature and the wind speed from the user. And then we've got temperature less than the temperature for the coat. That's one of the expressions. And then we've got the or, wind speed is greater than the wind speed for a coat. So if it's an or, that means that if this is true, the whole thing is true. And if this is true, the whole thing is true. So either piece is true. Down here, we're using an and. So for this where coat to become true, both these pieces must be true. So the temperature must be colder than the temperature for a coat, and the wind speed must be greater than the wind speed for a coat. Okay, so let's run this, and we'll get two output statements. Okay, so let's say that the temperature is 30 degrees Fahrenheit. That's pretty cold. And the wind speed is 60 miles per hour. It's almost a hurricane. Both cases say you need to wear a coat. So in this case, the or case says true. Obviously, both those pieces are true, and the and case would obviously say true as well. Okay, let's run another example here. Let's say that in this case, the temperature is pretty cold, but the wind speed is not so bad. So in this case, according to the first rule, which is the or rule, I need a coat because it's cold. The second rule says I don't need a coat because the wind speed in this case is too low. Okay, so hopefully that makes sense. You can see how powerful this can be. Just a really simple switch of a condition can totally change the logic, really depending on what we want. Remember, check those edge cases. Those are the ones where people tend to make mistakes on. Greater than and equal to. Sometimes you don't mean equal to, you just mean greater than, or the other way around. So testing is so important. In this video, we'll learn about C++'s compound assignment operators. These operators are very easy to use and commonly used in C++ code. The syntax for the operators is pretty simple. It's the operator you wish to use immediately followed by an equal sign. There are quite a few of these operators, but we'll focus on the mathematical operators. The bottom half of this table includes the operators that are used to manipulate bits. They're called bitwise operators, and I'll cover them later in this course. So let's look at the first one in the table, the plus equal operator. We apply the operator as in the example column. For example, left-hand side plus equals right-hand side. The meaning of this would be to increment the left-hand side by the right-hand side, and then store the resulting value in the left-hand side. We'll see a few real code examples in the next slide. All of these operators work the same way. For example, the multiplication equal operator multiplies the left-hand side by the right-hand side and stores the product back in the left-hand side. Let's see some examples. Here we see some examples of using several of the compound assignment operators. Let's look at the first example, a plus equals 1. This means increment the left-hand side by the right-hand side and store the result back into the left-hand side. So this is the same as a equals a plus 1. And it's another way of incrementing a variable by 1. The second example works exactly the same way, except that we'll be dividing the a by 5, then storing the result back into a. The third example shows how the entire right-hand side is evaluated before the operator is applied. In this case, we have a multiplication equal b plus c. This means multiply a by the sum of b plus c. Then store the product back in a. In the last example, we're incrementing cost by the product of item and tax. The best tip I can give you when you write these operators is to think of the right-hand side as being inside parentheses, and you'll always have it right. In this video, we'll learn about operator precedence and associativity in C++. C++ has well-defined operator precedence and associativity rules. Here's the table showing the precedence and associativity of some of C++'s operators. Note that this table is not complete. It only shows a subset of C++'s operators. You can find complete operator precedence tables online and in most C++ books. Note that there's two columns. The first column shows the operator. The operators on higher rows have higher precedence than operators on lower rows. So as you can see, the assignment operators are down at the bottom, as you would expect, and the parenthesis operator is at the top. Operators on the same row have the same precedence. So for example, you can see that addition and subtraction have the same precedence. I think precedence is pretty easy to understand. We learned operator precedence when we learned math in grammar school. It's the same idea here, except we have more operators to consider. The second column is the associativity column. This is the part that many times confuses students and even C++ programmers. Notice that associativity is left to right or right to left. Let's see what it means. So what's associativity all about? Suppose you have an expression with two adjacent operators and these operators are different, like we see in the first example. We can look for operators in the precedence chart, and if one of the operators has higher precedence than the other, then that's the operator that's applied first. This is exactly like we've been doing with our math that we've learned. But suppose the two operators are the same or they're different, but they have the same level of precedence. Now precedence doesn't really help us. In this case, we determine how the operators are applied by using their associativity. In the second example, we have the same operator, op1, used adjacently. If op1 associates left to right, then we apply the operator to expression 1 and expression 2 first. If op1 associates right to left, then we apply the operator to expression 2 and expression 3 first. Of course, you can always use parentheses to remove any doubt and be sure that your result is what you expect. Using parentheses is good practice with complex expressions. Let's see a couple of simple examples. In the first example, we have three operators: the assignment operator, the addition operator, and the multiplication operator. The precedence chart tells us that the multiplication operator has the highest precedence, followed by addition, followed by assignment. So I've rewritten the same statement on line 2, showing the order of evaluation by including parentheses. Note that the evaluation takes place in order of multiplication, addition, and finally assignment. In the second example, we again have three operators: the assignment operator, the addition operator, and the subtraction operator. In this case, addition and subtraction are of higher precedence than assignment, but they both have the same precedence. So in this case, we need to use their associativity to determine the order of evaluation. We see that plus and minus associate left to right. I've rewritten this example using parentheses to show the order of evaluation. Many beginning C++ programmers keep an operator precedence chart handy when they first start out with C++. After not too long, you get to know the operators, and this becomes second nature, just like using math precedence did the more we used it in school. Welcome to the Section 8 Challenge. For this program, I'm going to be using US dollars and cents, but feel free to use whatever currency system you're familiar with or you want to use. The idea here is you want to write a program that asks the user to enter the following. Ask them to enter an integer representing the number of cents. You can assume that the number of cents entered is greater than or equal to 0. The program then displays how to provide that change to the user. So in the US, we have $1 is 100 cents, a quarter is 25 cents, a dime is 10 cents, a nickel is 5 cents, and a penny is 1 cent. So in this example, suppose the user enters 92 cents. Your results will display that you can provide this change as follows: no dollars, 3 quarters, that would be 75 cents, a dime, which would be another 10 cents, that would give you 85, the nickel is 5, there's your 90, and the 2 pennies, there's your 92. As I said, feel free to use your own currency system. Also, think of how you might want to solve this problem using the modulo operator. When I give you my solution, I'll have two solutions. I'll have one without the modulo operator and one that uses the modulo operator, just so you can see two different ways to approach the problem. Quick hint, please don't just sit down and start coding this. Think about how you want to solve it. Write down some pseudocode. That's English-like statements so you can get your thoughts straight. Figure out what your algorithm is or your steps that you want to use to solve the program. So have fun. Make sure you test your program. Don't forget to test zero. Don't forget to test large numbers. And what I'm going to do is I'm going to do a couple of sample runs just so you can see how this works. So in this example, it says enter an amount in cents. So let's say I type in 92 cents. And the program responds, you can provide change for this as follows. $0, 3/4, 1 dime, 1 nickel, 2 pennies. Just like we would expect. As I mentioned, don't forget to test with zero. And we should get all zeros straight down the line. And let's say we want to test this with 267 cents. That's $2.67. In this case, we've got our $2. We've got 2/4. That gives us 50. The dime gives us 60. The nickel 65 and the 2 pennies 67. So there are your 267 cents. All right, so have a go at it. And when you come back, go to the solution section and I'll go over my solution. Good luck. Okay, so welcome to the Section 8 Challenge Solution. I hope you were able to solve this problem and I hope it was fun to do. And I hope you tested it and tweaked it, made it your own, added some features to it, and so forth. Let me just go through a couple of solutions. First, we'll do the solution without using the modulo operator. So I'm going to scroll up here, and let me just explain what I've got going on. Here's my main right at the beginning. Okay, so I've defined conversion constants. These are just simple integers, and it's the value in cents of $1, a quarter, a dime, and a nickel. Okay, so $1 is 100 cents, a quarter is 25 cents, and so forth. Then I've got another integer called change amount. This is what I'm asking the user to enter. All right, so let's suppose that we're entering 92 here, and we'll walk through a simple example. Here I'm declaring all the variables that I'm going to need. Dollars, quarters, dimes, nickels, and pennies are going to contain the number of dollars, quarters, dimes, nickels, and pennies that I need to provide the change. And then I'm going to have another variable called balance. And that's going to be a balance, a running balance. So every time that I figure out I need $2, and I'm going to subtract $2 from the original amount until I get down to zero. Okay, so that's my my algorithm or my solution is basically to determine how much of the highest currency I need and then subtract that and have a running balance until it becomes zero. All right, so let's do this example here. And I'm just going to write some letters over here. I'll write dollars, quarters, dimes, nickels, and pennies, so we can keep it running. And I'll have a balance variable here as well. All right, so let's start. We're right about here on line 57. And we need to figure out how many dollars are in 92 cents. Well, there are none, right? So what we want to do is we want to divide the change amount, which in this case is 92, divide that by the dollar value, which is 100 cents per dollar. In this case, that's going to give me a 0. Remember, we're using integer division here, so I'm going to get to 0, which says no dollars. Makes sense, right? Because I've got less than 100 cents. Now, I need to update my balance. Well, how do I do that? I decrement however many dollars times 100. Well, I had 0 here, right? So in this case, the change amount is going to be 92. And I'm going to subtract from that 0 times 100. Okay, so in this case, I'm not subtracting anything. My balance becomes 92. Okay, so that's the first step. Now we need to determine how many quarters we need. So I'm going to take that balance, which is 92, and I'm going to divide it by the quarters value, which is 25 cents. And that will give me a 3, right? 75 cents. So I need 3 quarters. Now what I want to do is I want to subtract that 75 cents from the 92. And in this case, I'm using a compound operator right here, the minus equals. So all I'm saying is balance equals balance minus the right-hand side. Well, the right-hand side is 3 quarters times 25 cents each, which is the 75. Okay, so I'm going to subtract 75 from the balance, which is going to give me 17. So that's my current balance. Now I can work on the dimes. How many dimes? Well, it's the balance, which is 17 divided by 10 cents per dime. So this is going to give me 1. So that's 1 dime. And I'm going to do the same thing here. Hopefully you can see what's going on. I'm going to subtract 1 dime, which is 10 cents each, from the balance. So I'm going to subtract 10 from the balance. Gives me 7. Now I'm going to figure out how many nickels I need. 7 divided by 5 cents per nickel. So I need 1 nickel. I subtract 5 from the 7, and I end up with 2. My balance is the number of pennies I need. I don't need to do any more calculations, and that gives me the 2 pennies. And we're basically done. So if we add up all of this, let's test this out. This is going to give me 0. This is going to give me 25 times 3, which is 75 cents. This will give me the 75. This will give me 10. 1 times 10, 1 times 5, and 2 times 1. If I add all those guys up, I should have 75, 85, 92. Exactly what I expected. Okay, so that gives you an example of one way to approach this. We'll do it really quickly with another example here. Let's say we wanted to use something like 267. So let me clear this, and I'll go through this one really quickly this time. So let's say it's 267 is the amount that the user entered. Okay, so here, how many dollars? Well, 267 divided by 100, right? 100 cents per dollar. That's going to give me $2. Then what I want to do is I want to subtract, I'll run my balance up here, those 200, which gives me 67 cents. That's my balance. How many quarters in 67 cents? Divide that by 25. That gives me 2 quarters, which is 50 cents. I'm subtracting 50 cents, and we're right back to where we were with the other problem where we've got 17. How many dimes? Divide that by 10. It gives me 1 dime. That's 10 cents. I subtract 10 from that. I end up with 7. How many nickels? Divide that by 5. It gives me the 1 nickel. And I've got 2 left, which is my pennies. Right? So this gives us, right here, 100 times 2. It gives us the 200. This gives me 50. This gives me 10, 5, and 2. Add all that up. I get 250, 260, 270. I'm sorry, 200, 250, 267, which is exactly what we started out with. Okay, now we can take advantage of something here. If you notice, if I have 267 and I divide that by 100, let's say, that gives me $2, integer division. But notice that I have a remainder. My remainder is 67, right? That's where we can use the modulo operator to rework this a little bit. So we'll do that next. Okay, so let's look at another solution. This time we'll be using the modulo operator. So suppose the user enters 267 for the change amount. And I've put all these on the same file. That way you can play around with both of them a lot easier. So in this case, I'm zeroing everything out, just like when we started. So I've got 267 cents is what the user has entered. And we'll just keep a running total over here for the dollars, the quarters, the dimes, the nickels, and the pennies. Okay, so how many dollars? Well, we divide 267 by 100 cents per dollar, and that gives us the $2. So we definitely need that. Now, rather than subtract the 2 times 100 from the 267 as we did before, we can take advantage of the modulo operator. So in this case, the change amount is 267 mod 100. Right? This gives us 2 with a remainder of 67. So the effect is exactly like subtracting 200 from 267. Okay? So what we can do is we'll keep our balance down here this time just to have a little bit more room. In this case, our balance is going to be 67. That's what we just assigned right here. Okay. Now, let's figure out how many quarters we have. Well, our balance is 67. Divide that by 25 cents per quarter, and that gives us 2 quarters. So now again, instead of subtracting 50 from 67, we could just use the modulo operator. Here I'm using the compound operator. So it's balance equals balance mod quarter value. Same idea. So balance is 67 mod 25 gives us 2 quarters, right? That's 50 with a remainder of 17. So our balance becomes 17. And then from this point forward, I think you could see what's happening. Our balance is now 17 divided by 10 cents per dime gives us 1 dime. And then we do the same modulo operator. So we're going to have 17 mod 10 gives us 1 with a remainder of 7. That's really what we care about, is the remainder in this case. How many nickels? 7 divided by 5 cents per nickel. It gives us 1 nickel. And then we do the mod operator one last time. We're going to say the balance would be 7, which is my balance, mod 5, which gives me a 1 with a remainder of 2. At that point, our balance is 2, which is the number of pennies that are left. And again, if we add this up, we're going to have $2 here, which is 200. We've got 50 cents here, 10 cents here, 5 cents here, and 2 cents here, which gives us 200, 250, 267. Okay. Another approach, to me, this approach, I'll clear this so it's not so cluttered real quick. To me, this approach, as I read it, looks easier to follow than the other approach, but they're both really doing the same thing. It's just a matter of preference and documentation. So that's it. I hope these two solutions were pretty close to yours.